Hello there, Mr. Sutton here, bringing you the AB Calculus 512 homework solutions on FTC free response practice. For this free response, they're giving us the continuous function f, which they actually gave us a graph of right here, and there's also this function g, which is going to be 2x plus the integral of f from -2 to x. So first thing they want us to do is find g of 0 and g of -5. Well, let's start with g of 0. Here's the g function, so let's just plug in 0 to x and see what happens. So that's 2 times 0 plus the integral from -2 to 0 of f. Well, 2 times 0 is just 0, so we don't have to worry about that. Now, the integral from -2 to 0, looking up here, that's the area under the curve of f from -2 to 0. And we see here that this is just a trapezoid. So we have a base of, let's see here, this is 2 plus a base of 1 divided by 2 multiplied by a height of 2. So 2 plus 1 over 2 times 2. 2's are going to cancel, so that just ends up being 3. All right, next we have g of -5 that we have to calculate. So that's going to be 2 times -5 plus the integral from -2 to -5 of f of t dt. So we've got -10. And also, let's see here, we're going from -2 backwards to -5. So that means that the areas are going to be reversed in terms of their sign. So taking a look at our areas, we have this area between -5 and -3. It's this triangle that's underneath the x-axis. Now, normally, since this is below the x-axis, this would be considered negative area. But since we're going backwards from -2 to -5 with our integral down here, that means that this area underneath the x-axis is now positive. So we're going to have 1/2 times a base of 2 times a height of 4. And then we also have this little triangle up here between -3 and -2. So because we're going backwards, this is now negative area up here. So we're going to have -1/2 times a base of 1 times a height of 2. And you could actually leave it like this because you've got all constants. But if we do simplify it, let's see here, this is going to be -10 plus, this is going to be 4 when those 2's cancel. So that's -6 so far. Over here, the 1/2 and the 2 cancel. So we have -6 minus 1, all of which comes out to -7. For this problem, they want us to find g prime of x in terms of f of x. So here's the g function again. Taking the derivative of this, 2x is just going to become 2. And this integral here, I'm using my FTC, plugging in the upper limit for the dummy variable. So that's going to end up being just f of x. Next, they want us to find g double prime of 4 and g double prime of -2. Well, g double prime in general is going to just be f prime of x. This 2 is gone because it's a constant, and then we just have the derivative of f. So basically, g double prime of x is just giving you the slope of this graph of f that they gave you up here. So when they ask for g double prime of 4, they're just asking for the slope of f at x equals 4. Well, let's see, we got 1, 2, 3, 4. Here it is, right here. So we just need the slope of that spot. Now, since this is part of a line, we just need to find the slope of this whole line. We can do that by doing a little average rate of change sort of calculation. So we can do -3 minus 3 over 8 minus 2. And you could just leave it like this since it's all constants. Or you could simplify it. This is -6 over 6, which is going to be -1. Next, we want a g double prime of -2. So here's -2, and we're asking for the slope right there. Now, that's a little trickier because that is a corner. So we actually can't find this derivative because that's going to be undefined at a corner. It's not differentiable. So I'm going to write g double prime of 2 does not exist because f has a corner there. On this part, they want us to figure out on what intervals, if any, is the graph of g concave down. All right, well, g is going to be concave down wherever g prime is decreasing. And remember, g prime is really just 2 plus f of x. So they didn't give us a graph of 2 plus f of x. They gave us a graph of just f of x. But in terms of increasing or decreasing, f of x and 2 plus f of x are going to be increasing or decreasing on the same intervals. Because this 2 plus, this is just shifting this graph that they gave you here up by 2. So that's not going to affect the slope at any particular spot. So we can say then that 2 plus f of x, just like f of x, is going to be decreasing on the interval from -2 to 0, so that's one spot, and also on the interval from 2 all the way here to 8. So therefore, g is going to be concave down on these same intervals. For this part, we were given the function h, which is g of x cubed plus 1, and we want h prime of 1. Let's start by getting h prime of x. That's going to be g prime of x cubed plus 1 times the derivative of x cubed plus 1, so times 3x squared. And since I don't really have a function for g prime, remember, is just going to be 2 plus f of x. So I can rewrite this stuff here as just 2 plus f of x cubed plus 1. And that's at least going to give me something that, since I know the graph of f, I might actually be able to calculate something with this formula written in this fashion. All right, so now that we've written it in terms of f, let's plug 1 into everything. And let's see here. We've got 2 plus, this is essentially f of 2. This is a 3 over here. What is f of 2? Well, that's the value at 2 on the graph here. So the x value 2 gives us back a value of 3 on the graph of f. So this is really 3 times 2 plus 3. And let's see, that's 3 times 5, which gives us 15. For this problem, we have this continuous function f with a graph of f given and a whole bunch of information. We've got 2 line segments. We have some areas that they gave us down below here. A and B, they said, were 3 and 5 for the areas. And they also gave us the formula for this little piece. This is an upside-down parabola given by this f of x function. So we want to know for the first part, oh, they also gave us the g function, which is the integral from -4 to x of f of t dt. So for the first part, they actually want to know g of 0 and g of 4. So we're going to use this g function right off the bat. For g of 0, we've got the integral from -4 to 0 of f of t dt. So I'm just finding the area under the curve of f between -4 and 0. So we've got this triangle area and this area A that we're going to have to add up. Let's start with the triangle. So that's going to be 1/2 times a base of 3 times a height of, actually this is also 3. And then this A area here, well, they told us that the area of A was 3. And this is below the x-axis, so this is actually a -3 that we're incorporating here. So we've got, let's see here, 9 over 2 minus 3, so 9 over 2 minus 6 over 2 is going to give us 3 over 2. So that's g of 0. Next, they wanted us to figure out g of 4. So g of 4, what's that going to be? That's the integral from -4 to 0. Now, to save ourselves a little bit of time, we already know what the integral from -4 to, well, actually, this is -4 to 4. We already know the integral from -4 to 0. That's 3/2. So really, g of 4 is just going to be this 3/2 plus whatever area is left over between 0 and 4. So I'm just going to write 3/2 there. We've already accounted for the area between -4 and 0. And now we have this area B, which they told us was just 5. So we're going to add a 5 on there. And we also have the area under this f function. So I'm going to have to take the integral now from 1 to 4 of f of x, which is this whole -x squared plus 5x minus 4 function. So to do this, I'm going to just use my fundamental theorem, take the antiderivative of this, and plug in 1 and 4. And I'm also going to clean things up a little bit with this 3/2 and this 5. This is really 3/2 plus 10/2, or 13/2. And now taking my antiderivative, using my reverse power rule, this first exponent bumps up to a 3. Dividing by that, we have -1/3 x to the 3rd. And this x here becomes x squared. Dividing by 2, we have 5/2 x squared. And then the reverse line rule gives us -4x, and all of this evaluated from 1 to 4. So we have 13 over 2 plus all this stuff with 4 plugged in, minus all this stuff with 1 plugged in. At this point, you've got nothing but constants. So if you wanted to, since this is numerically equivalent to the right answer, you could actually stop here and you would get full credit. But why would we stop here? I mean, why not simplify when there's no good reason for simplifying? So let's go ahead and simplify. I mean, who knows? Maybe we'll need it for a future part, maybe not, but it's not the real AP test, right? So let's just go ahead and simplify. This is one of those kids don't try this on the real test sort of things, but here we go. So we have 13 over 2, and what else do we have here? This is going to be negative 64 thirds. Next, this is going to be, let's see, 5 halves times 16. 16 divided by 2 is 8. 5 times 8 is 40. This is minus 16. Over here we have plus 1/3, minus minus. Then we have a minus 5 halves, and this is going to be a plus 4. All right, let me add up all the non-fractions. So we have 40 minus 16 is 24. And then adding 4, that gives us 28. And let's see here. We have negative 64 thirds plus 1/3. That's negative 63 thirds. And we have 13 halves minus 5 halves is going to be 8 halves. So hold on a sec. 63 over 3, that's 21. So this is 28 minus 21, which is 7. And we have 7 plus basically 4 here, which gives us the nice round number of 11. Well, that was neat how it just worked out to that nice whole number. On this problem, they want us to find the absolute minimum value of g on this interval. So we know that the absolute min here is going to happen either at one of the endpoints, negative 4 or 4, or at a critical value for g. So for critical values, we need to do g prime. G prime, using our fundamental theorem here, is really just f of x, because you just are plugging this upper limit in for the dummy variable. So where does f of x equal 0? A lot of places. We have this endpoint over here and this other endpoint, but we were going to test those anyway, so we don't really care about those. But we have also some critical values for f at negative 1, 0, and 1. That's potentially a lot of places to have to test. To narrow this down a little bit, we actually only need to consider the relative mins. The only place where f is changing from negative to positive is at x equals 0. Since we only change negative to positive at x equals 0, since that's our only relative min, that's the only value we're going to test between the endpoints. Because let's think about this. If a critical value is either a relative max or at least not a relative min, if it's not the smallest value in its immediate area, how is it going to be the absolute smallest value for the entire graph? I mean, if there's other values right next to it that are smaller, then you definitely don't have the absolute min. So at the end of the day, using the candidates test, we only have to try out negative 4, 0, and positive 4. All right, well, let's start with negative 4, g of negative 4. That's just the integral from negative 4 to negative 4 of f of t dt. Now, since we have the same lower and upper limit of integration, this is an empty integral, basically, no area. So this is just going to come out to 0. Okay, well, let's do g of 0 now. If this is feeling familiar, it's because we actually calculated g of 0 back in part A. You might remember it was 3 halves. Well, that only leaves one more value to test out, and that's g of the other endpoint, g of 4. And that one we actually also calculated in part A. And I made a big deal about, you don't have to simplify this because it's numerically equivalent. But for this part of the problem, you have to simplify it. You have to simplify it enough so that you can compare it to 0 and 3 halves. And when we simplified g of 4 in part A, we came up with 11. So comparing these three things, we just want to pick the smallest value, and that ends up being 0. So our absolute min then is just 0. For this problem part, we want to know all intervals on which the graph of g is concave down. So what we're really asking here is, where is g prime decreasing? We would say, where is g double prime negative, but it's harder to talk about the graph of g double prime. G prime we can get to pretty quickly because g prime, remember, is really just f of x. So all we have to figure out is where f of x, which we have a graph of right here, is decreasing. So looking for where we're going down, negative 2 to This spot right here is our first interval. Now what is this spot? Well, they said that we had horizontal tangent lines at x equals -2, or -1/2 rather, +1/2 and 5/2. So that's really giving you this x value up here, and this x value over here. So our first interval of decreasing is from -2 to -1/2. And then we have another interval of decreasing from +1/2 down here to 1. And then finally from 5/2 to 4. Now we're not done with the problem. All we've said is that g prime is decreasing on these intervals. We actually have to finish it here. This allows us to conclude that g is concave down on these three intervals. For this free response problem, we have a function of f such that f of 0 is 20, and the first derivative of f satisfies this inequality where f prime is always between 0 and 7, and we've even got some selected values of f prime in the table here, which, as you can see, all of these f prime values do fall between 0 and +7 inclusive. They also said f has a continuous second derivative for all real numbers. So basically we're saying f is twice differentiable, and a little bit more than that because the second derivative is continuous in addition to existing. All right, so first task, we want to use a midpoint Riemann sum with three subintervals of equal length, indicated by the table data here, to approximate f of 6. So our general setup here, since we know f of 0 and we know the derivative of f, we can use the FTC to talk about an expression for what f of 6 should look like. We can say f of 6 equals f of 0, namely 20, plus the integral from 0 to 6 of f prime of x dx. Now, where we have to approximate here is we don't actually know what f prime is doing algebraically. All we have is some table values for f prime. So we are going to have to approximate it with some kind of Riemann sum. Now, in part A here, they asked us specifically for a midpoint Riemann sum. So let's go ahead and get that. So I'm going to write that all of this is approximately equal to the following. So we have the 20, and now for the actual midpoint Riemann sum. So these are all going to be areas that we're adding together. The base on all these areas is going to be 2 because we're going from 0 to 6 with three subintervals of equal length. So that's base of 2 for each of these rectangles. And for the height, I'm going to be picking the middle value for each of these because this is a midpoint Riemann sum. So my first rectangle, from 0 to 2, I have a base of 2 times a height of 3.5. Again, we're picking the middle height value. And then for the next one, I have a base of 2 times a height of 0.8. And then the last one, base of 2 times a height of 5.8, which is, again, the middle value that we're using. So this is numerically equivalent to the right answer. You could actually just stop here. But if you wanted to simplify it, we can think of this as being 20 plus 2 parentheses, 3.5 plus 0.8 plus 5.8, all added together. And if I add these three things in here together, what does that come out to? Well, let's see here. Let me just add the decimals first. 0.5 plus 0.8 is 1.3, plus another 0.8 is 2.1, plus a 3 and a 5 is going to be 10.1. 2 times 10.1, that's 20.2, plus another 20 is 40.2. Again, you could have stopped up here, but I don't know, maybe you just feel the need to simplify. For this problem part, they want us to determine whether the actual value of f of 6 could be 70. So this is a little bit tricky because we don't know a whole lot about the f function other than f of 0 is 20, and again we have some values of f prime in this table. The key here is they told us that f prime is guaranteed to be between 0 and 7 for all x's on the interval 0 to 6. So we basically have to find out like kind of a best case and a worst case scenario for what f of 6 could be and see if 70 falls in that range of numbers. So what's the smallest value that f of 6 could be? We calculated f of 6 by doing f of 0, so namely 20, plus the integral from 0 to 6 of f prime. Well, what could the integral from 0 of f prime at minimum be? Let's suppose that f prime is exactly 0. Then f of 6 would be 20 plus essentially 6 times that height of 0. So that's the minimum value that f of x could be. Now, on the other hand, let's say that f prime is 7 all the way across, which is its greatest possible value. Well, then f of x could be 20 plus 6 times 7. This would be the maximum possible value for f of x. So we see here that f of x is going to fall somewhere between 20 and, let's see here, this is 20 plus 42, which is going to be 62 over here. Since f of x is at most 62, it cannot possibly be 70, so that shows what they wanted us to show here. For this problem part, we want the integral from 2 to 4 of f double prime of x dx. So we don't know a whole lot about f double prime, but we can use our fundamental theorem and take the antiderivative of this, which is just going to be f prime, and then we just have to evaluate that from 2 to 4. Okay, well, f prime of 4 minus f prime of 2, what's that going to be? We actually have those values in the table up here. F prime of 4 up here is 1.7. F prime of 2 back here is 2. So 1.7 minus 2, I mean, if you wanted to simplify it, you actually don't even need to, but this is going to be negative 0.3. For this last part of the problem, they want us to find the limit as x approaches 0 of this expression. Now, this is one of those where you can quickly do a mental check and kind of see where you have to go with the problem, but then you have to do a whole bunch of work to actually justify where you're going. So just doing a quick mental check here, if you do f of 0, we see here that that's going to be 20. And if you plug 0 into the x value here, this comes out to 20. So you got 20 minus 20, which is going to be 0 in the numerator. Down here you have 0.5 times 20, which is 10. Subtracting 10 is going to give us 0 in the denominator. Of course, we're not going to write 0 over 0, and there's some other stuff we need to do first. But we see this is going to be one of those indeterminate forms. So we're going to have to use L'Hopital's rule on this one to come up with an answer. All right, to sort of set the groundwork for all of that, the first thing that I observe is that f double prime is continuous. They said that f has a continuous second derivative, so that's what this is saying. Now, why is this important? This is important because if f double prime is continuous, that means that f is differentiable, and so is f prime. So what that means is that f and f prime are both continuous. Now, why do we care about that? Well, this is important because it means that the limit as x approaches 0 of f of x is going to equal f of 0, which is important because at some point I'm going to have to find the limit of f of x as x approaches 0 when I'm doing this problem here. And it would be awfully nice if I could say that, hey, this is just going to be what I get when I plug 0 into the f function. Because before we write all this stuff, we haven't really established that we're allowed to say this. Now, also, while I'm kind of on the same line of thought here, this stuff also means that the limit as x approaches 0 of f prime and f prime of 0 are equivalent. So when I want to take the limit of f prime at 0, I can now just plug 0 into f prime. All right, now that I have this option, let's go ahead and actually take the limit of the numerator and the denominator separately. Whenever you want to set up L'Hopital's, you have to show that these limits are independently both 0 or both infinity. So for the numerator, the limit as x approaches 0 of f of x minus 20 e to the x. Again, limit of f of x as x approaches 0, we saw that that's really now just f of 0, which they told us right away here was 20. And if I plug 0 in for the x here with the e function, that's 20 times 0, which is also 20. 20 minus 20 comes out to 0, and now we've shown it. We also need to look at the limit of the denominator. Again, this is really just 0.5 times f of 0, which is going to be 0.5 times 20, which is 10. Subtracting 10 from that also gives us 0. Since these are both 0, that means that we can now use L'Hopital's rule, which basically means that this limit up here is going to equal the limit of the derivatives of the numerator and denominator. And we know the derivatives are going to exist for f because f is differentiable because f double prime is continuous. So we can rewrite that limit now. Limit as x approaches 0 of f prime of x minus 20e to the x. 20e to the x is its own derivative, so that's kind of nice. And down here we're going to have 0.5 f prime of x, and that's it. The minus 10 was just a constant, so now it's gone. All right. So again, when we take the limit as x approaches 0 of f prime, we saw up here that that's the same as doing f prime of 0, because f prime is shown to be continuous. So what is f prime of 0? Well, f prime of 0 up in the table here is just 4. So this is 4 minus 20 again, because you're just doing 20 times e to the 0. Down here we have 0.5 times 4. So this is going to be negative 16 over 2, which is just negative 8.